So I'm going to talk about denoising diffusion models, or also called score generative. So I'm from the University of Potsdam. I'm doing my PhD in this very exciting topic in the intersection of the mathematical theory for this and a bit of application, but this will be more of an applied talk, and we will learn how to implement this kind of model by ourselves. So, and these models are, I mean, many of you have probably heard of them already. They're quite on vogue right now. It's the Stable Diffusion stuff, or DALL-E, where you can like enter some weird stuff and then it will generate an image for you of whatever you entered. And actually, the nice thing is that, so things like this were possible for a few years now, but with this algorithm, it took off, and now it's possible to even do it on your home computer normally, and it also has very, very nice mathematical theory behind it. So you can like come from any side and have some nice interaction with this topic. And also, so I prepared all of this as a Jupyter notebook. So I'm going to try to run it live. I also have it as a HTML in case I mess something up in between. But you're all invited to ask questions in between at any point to make this kind of interactive. So I have like a bit of buffer for questions. Okay, so let's start very, very general first. What do generative models do? So these denoising diffusion models are algorithms of the class of generative models. And generative models have the task that you're given some samples from a measure that's very mathematical, and I mean in real life it just means you have like many, many images of some unknown distribution. Maybe all cat images, all dog images is the typical example from the internet. And now you want to generate more images from the same measure. So you want to generate more dog images, more cat images that look like the input images, similar but not exactly the same. And you want to do this because these things are often then used in downstream tasks like super resolution, so you can put in a low resolution version of the image and you get a higher resolution. You can cut out a part of the image and it will fill it in, these kind of things. Yeah, and so the very basic idea behind denoising diffusion models is that you have your data distribution, which is like, for example, images of all dogs. This is, oh, maybe I'm going to do it like this better. Images of dogs, which is a very complicated distribution in some sense, right? It's not easy to describe or algorithmically implement something that will output an image of a dog. And then what you can do, though, is transform it to noise. And that's quite easy. Basically, I mean, on a computer, it's just adding noise. You just sample random noise and add it to the image. That's it. And then from this process, you want to learn how to reverse it. So now you want to learn, because you're like basically observing this process very often, and now you want to learn how to reverse the process of going from here back to the image, or here I have it on the right. And if we are able to do this, then everything is good, right? Because producing noise is quite easy. You just sample random vectors on your computer. Every computer can do that. And if you can do this process, then you can input this random noise to the process and you will get a new image. So, yeah, and let's just do that. I mean, that's not a hard task, right? Yeah. So here I'm import yax.numpy, SJ. I'm not going to walk through this, but these are the inputs, but nothing very exciting. So Jax is this new Google machine learning lab. I don't know what the background of the full audience is, like how much people have already done machine learning and whatever, but Jax is like this new, very cool machine learning library from Google. So alternative to PyTorch and TensorFlow, basically. And also, if you already know, it has actually, what's really cool about it is that's also why I'm calling it JNP, like NumPy, because it has the exact same syntax as NumPy. So if you can program in NumPy, then Jax, you can basically also program in Jax, and you just have auto-differentiation functionalities and can take gradients and whatever, optimize. Okay, helper function, not very interesting. So now let's create our simple data distribution that we want to sample from, because I'm going to run the stuff on my laptop here, and of course doing it in this high resolution kind of thing, this would not be possible. I would need a GPU for it. But I mean, But for like lower resolution images than this, it would actually be possible maybe on your home desktop tower already. If you have a graphic cards or something like this, then these things work. But for here, because it's on my laptop, no GPU, no nothing, and I want it to run fast, and it's way easier to implement it here in low dimensions. We're just going to do a very simple example. So we have a data distribution which is given as a sphere, and we have some samples from it. So the true data distribution that we want to like recover are samples from a sphere, which is like a bit of a complicated distribution already because it's not everywhere in the space. It's only on very specific areas of the space. And now we also say we only have 10 samples from this distribution, right? These are the 10 samples. So these are our examples that we want to input into our algorithm, and we wanted to learn to output more points that look like these points. And optimally, it would be just points on the sphere, right? So we would like to recover the full thing, which would be magical. Okay. Nothing very exciting happening here too. So this is just a like very simple neural network, like really the simplest that you can think of. I'm not going to go in much details about neural networks, but for the ones that know about it, it's just like fully connected layer, like a few fully connected hidden layers. Like the first architecture everyone will come up with. The only choice is maybe the activation function, but that's, yeah. Maybe I should also execute the code. So, yeah, everything. Okay, and now comes the loss function, and it's really simple, right? Okay, maybe don't make changes now anymore. But so the loss function, what it does is you get your model, your current predictor. So what you're training, what you want to learn is a function that gets noise and outputs the data. Or in this case, it will get two-dimensional noise vectors, so samples from a standard normal distribution in 2 dimensions, just random in both, like a vector with 2 coordinates, both completely random, and it should output a sample of the distribution, which would be something here like on the sphere. This is what we want, right? And we have these 10 samples. And what the loss function does is you get some data that you know that is from your true data generating distribution. Then you generate a normal sample. So yeah, normal distribution with the same shape as the data. And what you then do is you forget most of the data because you want to, basically what you want to do is like, it would also work without the 0.01 here, the thing. This is what I was also just wondering about why I left that there. But what you do is basically you have your original data and you add some noise. Or actually maybe you also want to forget some of your data, so you want to rescale it to make it smaller, because otherwise if we would have a distribution that would be all scattered around space here, and then we add like normal noise here, we will end up with a distribution of points that is everywhere in the space. And therefore what we want to do is like we want to take the old thing, kind of forget it, and add noise, so that it really maps the old data to just the standard normal distribution, right? So you can think of it really as just trying to contain the same size. If I'm going too fast in anything or too slow, please tell me, or if you have any questions. Yeah, so sample normal vectors, that's easy, and now add your noise to the data, and then what the model should do is it gets the noised data. This is now very similar to just noise, right? Because nearly nothing of the old data is left, and we just add noise. And what we wanted to output is, actually we wanted just to output the data. So this is just the squared error, right? So we take the output of the model and then compare it to minus the data. There's a plus, it could also be minus, whatever. So we just wanted to predict the data that we had before, right? which is exactly what we like. And if it manages to predict it, then the loss is 0, so perfect. And if it makes a mistake, so actually the model gets the noise data, but doesn't really predict the data, but something else, then this loss will be bigger than 0. And if we now take gradients of this function and do whatever optimization algorithm, we will optimize the model to output from noise data normal data again. Yeah.
Don't we then learn the negative data? So like if you just add it, don't you learn?
Yeah, the thing is, so yeah, I mean I can also, so what you actually do is normally learn the noise here. I made some tests in the end, but in this case we can also keep it like this because our data, is actually symmetric. But we can also make it a minus. Like, you're right, in this case it should be a minus. Later, the thing is what you normally do is instead of predicting the, from this predicting the image, you predict the noise that was used to create this, and therefore because I'm later than, and then you want to predict minus the noise, but we will come to that. But let's make it a minus for now and hope nothing blows up, but I think it should be fine. I know, I have the noise, well, I just changed that, right? Yep. Yeah, okay, so this was data, and now it's data minus output. Okay. Okay, and let's train now. This is also not really, I mean, this is just every time, basically take the gradient of this, like put all the data that we have in there. It's only 10 data points, so we can put all of it in there. Get 10 new samples, so add noise to each of the 10 samples, try to predict it back, calculate the loss, take the gradients, and yeah, optimize your model. Yeah. This runs on my notebook here without a GPU. And now we sample the model that we have. And we see it doesn't work. So we can also maybe, because this is now also predicting the noise, but it's, so data is what we're actually predicting, and then, I know, was I predicting the data? Yes. Yeah, it just predicts a 0 in this case, which means it it predicts. No, it does make sense, I think, because, oh wait, what does it? I mean, maybe it's better to just change it to the old formula. Oh, what did I just change here? Wait. So this doesn't work in any way. This is not just now not working because there's this mistake, but I actually think it's right that it now maybe predicts a 0 because this is something that happens frequently. It will just learn that everything goes in that direction, especially because I have such a symmetric thing, but it was looking nicer before when it was just mispredicting all the noise, actually. Let me just try to do this for a second. And now you have the chance to interactively ask questions.
Do you know normalizing flows?
Mm-hmm.
So there's somewhat similar that you have a base distribution and then you apply a set of invertible transformations and arrive at a desired probability distribution. In what sense are diffusion models different from normalizing flows?
We will see that in the next step. But it's a good question. So, I mean, the summary answer to the question is, in normalizing flows, you just say, I want some model that goes somehow from image to noise and back, or from distribution to noise and back, and you learn both ways. both you have an encoder and a decoder. And what's really the main difference with these models is that the encoding part is fixed. You really say, this is the path I want to take towards the noise, I fix this, and now I just learn the decoder. And this makes things easier, because in normalizing flows you have to pass the gradients through all of the layers in some sense. And here you don't. You can, but we will come to this in a second. Let me see, and thanks for the question. If I can. So if I just do the noise, so now it predicts the noise, then this is the noise, and what I then want is because I here took it 100th noise data, so how does this data is equal to 100 times noise data minus noise, right? Okay.
Minus noise.
Yeah, thanks. Yeah, also doesn't look really good. But I mean, this is to be expected. This shouldn't work. Like, this was planned for it to not work. You see, I also already have the heading. So if anyone has an idea, does anyone have an idea what we could improve? I also wouldn't, but what you can do is just add more denoising steps. So what they do is basically, okay, so this doesn't work, so what we do is we add more intermediate distributions, right? We don't just learn the true distribution and then we go to the full noisy distribution and learn this maybe quite complicated transformation. But what we do is we have like very many intermediate distributions, all with a bit of more noise. And then we basically try to learn the same thing, but the estimate that we use, that we get from here, what this should be, we only use it a tiny bit. So we don't actually fully move from the noised version then up to the actual image, but we just say, okay, like try to denoise this. This is probably a very bad guess, as we saw here, but maybe it goes in the right direction at least. And then we use this intermediate noising scale to go a bit in the direction of the image. So we basically multiply it maybe like with 1/5 or something here. Now we have a better denoised version of our image, so like a bit of a better guess, and we do the same thing again. We try to denoise it again with another model that's now trained not to go from full noise to there, but to go from nearly noise to there, and then we go to here. And then we also use this prediction, but just use this model, this noise, and add a bit of it, of the prediction that we get from this to here, and then we already have this, and we repeat this. So, and there are some formulas here now. Sorry. What you do is, so this is the forward direction. So now going from here to here, how do you define all of these intermediate distributions? And you do that by this transition kernel, or like this transition. So given an image at time t, so at time 0 it's just the true training data image, you get the next sample by a normal distribution that's centered at xt, but multiplied with this constant, which is a bit smaller than 1, so you forget a bit of xt, and then you have a little variance in the normal distribution. So this is just writing it as like how you transform, but in a computer how you would implement it is just you take your old sample, you multiply it by a number that's a bit smaller than 1, and now you add some standard normal noise, multiply it with the square root of the variance, so to add like a little bit of noise. So each time you forget a bit more new noise, forget a bit more new noise, right? And it makes sense that this, after time, should lead to just noise. So this is just a one-step transition thing, and what's actually cool, what we will use in the code in a second, is that we can also now, if we would now want to get a sample from this distribution, just like we input an image, and for the training of the neural network, we will then want to like quickly generate, like give me this image and then give me maybe a noised version of this step or of this step or whatever. And we don't every time want to start with the noised image, go here, go here, go here, go here, and do this full path. But we would rather just have a function that takes us from here directly to here or whatever. And because these are very simple transitions, actually we can calculate calculate this, what it happens like if we apply these transitions one after the other. And then we see that from x0, so if you have an image, then the distribution of, for example, this one here, here is of course now an x0. Is then just x0 multiplied with a constant that's maybe now quite smaller than 1, because it's basically the product of all the steps that we had to do. So we define these 1 minus beta is like the product, is like how much we scale it down. Beta is like a small number, so 1 minus beta is a bit smaller than 1. Each time it's forgotten a bit more. And now the alpha I are just the product of all of these. So if we do 5 steps, we want to apply all of this at once. And the same thing holds for the noise. So, yeah. Okay. And why is it so complicated? Why is it 1 minus beta instead of beta? And then I multiply over the 1 minus beta. I also don't know. It's just the original notation that they introduced in the paper. So this is really how they introduced it in the, like one of the breakthrough papers, basically. So after you've heard this and memorized it all, you can really go off and read the papers and know the notation already. Now the question is, of course, how do we choose these beta and how do we choose these alpha? And this is actually quite a complicated question, like how do we choose them for optimal performance? And there's no real theoretical answer yet, but there are like huge empirical studies from where they just like tried different noising schemes and whatever, and some worked quite well and some worse. And this is just one of the schemes that worked a bit better, because the question is, of course, how fast do you want to go to noise very fast, or do you want to actually keep your original image for quite long and only transition to noise in the end and stuff like this? And all of these actually, like this really makes a change in how well the algorithm works, at which point how fast. And what you want to do is actually take very small steps in the beginning, which is maybe also intuitive, right? So want to like keep at the original image for quite a while and then in the end transition to noise quite quickly. But that's just an aside. Okay, so this is just a function for getting like the different beta value. Like, so I give in an n, which is how many steps do I want to take. Here there were 5 steps taken, or actually 4 steps taken, because it's 5 images and this is the original one. So how many steps do I want to take? And then it will output all the betas and all the alphas, right? And the betas is really just a simple function. I mean, don't think about it too much, but it's basically something very similar to beta min plus 1 over n, and then beta max minus beta min times e, where e is like how many steps you want to take. So you linearly increase the step size, the betas, and go from beta min to beta max. We have a small caveat, but yeah. And then the alphas is really just taking the product of the betas, so exactly this formula. Now let's get 100 steps actually. Oh. Okay. Wait, actually let's try with less, because I was before wondering why this already worked so well, because I wanted it to work not as well as it did, but maybe because I was taking 100 noising steps already. So let's see. Okay, new loss function. Very similar to the old one. The only difference is now we pass in the different time scales that we have, the different alphas. And then we just, for each of the data, and we again pass in the 10 data points. And for each of the data points, we now pick a random alpha, which is like which of the levels do we want to go here to, like, oops, sorry. Yeah, I'm not going to use this, I think. So where do we want to land, which is like which alpha? The alpha t is like the noising schedule. So we just pick the random alpha here, basically, yeah, that's it. And then we again sample standard normal noise. And what we do is then, okay, the noise data is now data times alpha, square root, plus noise times 1 minus alpha square root. Yeah. And this basically lets you forget again. Yeah, exactly. It lets you, so if alpha is very large, so alpha will be, or for later indexes, so if you pick a late time index basically, then alpha is already nearly to 0. That is quite close to 0 because you took all these steps, 1 minus beta, 1 minus beta, 1 minus beta, 1 minus beta, you multiply them all, and now you have a very small number, which is a small alpha. So then you forget most of your data, because this will just be nearly 0, and you nearly only add noise. This will be then nearly 1, so this will just be 1. And for small alphas, you will get, for small t indexes, which means alpha is nearly 1 still, it's like just 1 minus epsilon, whatever, then you will still retain most of your data and just add a little bit of noise. This is how we noise our data now. And then we output again, so we throw this into our model, the noise data, and we want it to output the noise that was used. And you can also actually try to use it to directly predict the data. And probably in this simple example it would work. But in general for images it's empirically observed that it's better to predict the noise. So, yeah, and you can use both in the same way. So now we predict the noise. And now we compare the output of the model, so of our neural network, to the actual noise that we used. And we want it to be minus the noise in this case. Well, so you could also do plus the noise, of course. It's just in the continuous time, we will come to it in a second actually. It makes more sense to do it this way. You could, of course, also learn minus, like plus the noise instead of minus the noise, and then just when you sample, also switch the sign. It doesn't make a difference. It's just how it is. Okay. Again, neural network, very similar to last one. The only difference is now that the network also takes a time component, not only a space, because the network, so the denoiser, will know where it is, right? So we will input it this and say, okay, and the time scale is here so that it knows, okay, this is made, like it can learn if t is high, or yeah, like if the noising schedule is very big, then it means that it has to denoise a lot, and for smaller t, it has to denoise less. So we give this as an input to the neural network, here with the t, exactly. And otherwise, it's still a very simple, fully connected thing. Okay, then we train again. Oh no. What did I change? Wait, let me just run it all again, because I know that it... Otherwise I have to use the copy from before I changed anything here. Where is it training? Is it running at all? No, here. Yeah, here, okay. So train this. Still doesn't work. What did I change? Does anyone know what I changed? Okay, let me just then close this. Don't save it. Oh no, but I saved it. Why is here again? No.
You opened the one with which was changed a minute ago. There was also
Okay. No, but this is the HTML. I mean, this is my backup solution for exactly this case. But then I can't execute the code anymore. But we can also just say we're past that now. Wait. Yeah, okay, let's go with this. Okay, so this I ran before this without doing some changes live. Okay, this is how the output looked there, although it could have something to do with what I'm predicting. But this, yeah, okay. Now let's go to the step that we're currently at. Again, we're just learning the same thing. So this is a very similar training loop to before. Yeah, the only thing is that we now input the different noise scales that we wanted to learn. Yeah? And actually it works. So now what we're doing with sampling is it's similar to before, although this is where it got a bit more complicated than before, but basically we're just going backwards. We will sample in the beginning just some completely random normal noise. Nothing's happening. And then we're going through all the betas and alphas, and what we're doing is at each step we're applying the model to our current estimate to get a denoised estimate of our data, and then we update the data that we have by basically, like, there's a way to derive this. I won't do it now, but what we do is basically take the old noise data and then we add a bit of our denoised thing. But we also scale it again with these beta and alpha to just like move it a bit in that direction. So we don't want to fully go there, we only go a tiny bit every time. And how much is, you can actually exactly calculate how much you should walk from how much you also noised in the beginning, right? So you know how much you noised in the beginning in each step and you want to like denoise in the same amount. Yeah? And this is quite exciting, I think. So because, I mean, we really only gave it 10 samples, right? And now it has the complete sphere, which is, yeah, I mean, it's still, I don't know, it still baffles me like how it does it. But yeah, if you develop theory on why they are able to do this, that's the holy grail, I think. Yeah. So, okay, it seems to work. And we want maybe higher sample quality, or just want to change it up more. And what could we do? This, exactly. Thank you for saving this. So we're adding more denoising steps. And what we're doing is, so this is the same dog image as before, but with very many denoising steps now. And, no. Now you're missing all the nice equations, right? Here, let's do the equations from here. No. So actually, and if you like, so this is if you have no clue of ordinary differential equations or stochastic differential equations, this is not really necessary. It's really, this is also how the algorithm was. You can implement the algorithm without any knowledge of that, like really with this intuition, and this is what makes it quite beautiful, that there are like so many ways to go at this algorithm. But if you know this kind of stuff, then actually this is like a bit, at each time you take xt plus 1 is basically something like xt minus delta t times xt. So you're like decreasing xt a bit, and then you're adding a bit of noise. And if you're letting these step sizes go to 0 and do it like faster and faster, you can actually exactly find out what that will converge to. And it's a stochastic differential equation, and this is just the continuous time formulation of the same thing. So it's really like, I want xt to change by like forgetting a bit, like in an ordinary differential equation, it would just be the derivative of xt is minus xt a bit, which will get you the exponential function and something like, but yeah, so forget a bit of xt, add a bit of noise. Just this is in the continuous time limit, so very, very like infinitesimal small time steps. And what we do at each time then is, if S is our model, we want to predict the noise that was used to create xt, and you can exactly write down how xt will be created. I won't go into too much detail about this, but the cool thing is that you can actually rewrite this noise, this loss function that we're using, it's equivalent to this loss function, where you now actually are optimizing again against not the noise, but actually you want to get the score of the distribution of xt. So pt is the distribution of xt, really at each time. So at time 0 it may actually be ill-defined, but at each positive time you have some nice distribution, and then you can actually take this, the score of it, and you can see that the loss that we had before is equivalent to trying to approximate this. And this is really nice. For me, and for many others, I think. So, and another thing, another way to see it is also that you can rewrite this thing as a conditional expectation, which makes it a bit more intuitive, because this score can actually be written, this is called Dup's formula, as, no, Tweedy's formula, sorry. Tweedy's formula as basically conditioned on that you actually know xt. So here should be xt is equal to x. You know that xt is equal to x. What do you expect the difference of x0 where you started, so the original image, and xt to be? So predicting the noise. So this makes really sense that this one is equivalent to this one, and then you can also show that these are the same, and this is maybe also a nice way to see it. And also this formulation generalizes better to different kind of things. Maybe I will say a thing about that. I don't know where the time is currently, but yeah. Yeah, and then the cool thing is now you have the reverse process, and you can see that the reverse process will also fulfill an SDE. And it's just this SDE, which is basically just so basically also what we did before. We, in some sense, we revert what we're doing here. Here we were forgetting a bit of the data. We had this minus 1/2 of xt. Therefore, now we have a plus 1/2. It's the same thing when you run an OD, like an ordinary differential equation backwards, and then you add some noise in the same way that you did before, but you also have this term which is basically moves it a bit towards denoising it in some sense. And you can also write it as an ODE, because if you leave this out, because at this, what you're doing here is basically at each step, you're like denoising a bit, but you're adding new noise, right? Denoising a bit, adding new noise, denoising a bit and adding new noise, and this will work actually. You like, because this is formally correct and everything, but you could also just, instead of adding new noise at each step, just denoise a bit less. To make it in the discrete setting again, and then I'm also done with talking about these equations. The difference is that what you can do, and this is also how it's algorithmically then sometimes implemented, you can either basically take from here and go denoise to here, and then add a bit noise to be here again. Denoise towards here, add a bit noise to be here again, denoise towards here, add a bit noise to be here again. And this is what this stochastic differential equation in some sense amounts to, like always denoising a bit and adding new noise. But of course, you could also just not add new noise and just denoise a bit, denoise a bit, denoise a bit deterministically. And then it's really like up to you what you prefer. I prefer the stochastic differential equation, and it's also the one that mostly works better empirically, although, yeah. But this one has the huge benefit that this is used if you want to do density estimation and stuff like this, because if, also like a small side thing for the statisticians and people who love the density estimation, if you now want to if this would be something continuous and you want to now get a point and you want to know how probable was this new point. Like, is this an image of a cat? Like, how probable is this under your distribution? Then with the SDE formulation, it's really hard to get the original point where this might have stemmed from. But with this formulation, in some sense, just very heuristically now, with the ODE formulation, you can basically then start at this point, run this deterministic path, and now you get a sample from the normal distribution, and you can just look how probable was this point. And then you know how probable was this point. So this is why this is really beneficial. Although for just sampling purposes, it seems that this is working better. And now everyone can do their angle of attack. So you can do discrete time, you can use the ordinary differential equations, stochastic differential equations, optimal control, which is now Lorenz is not here, I wanted to name drop him. He has a very nice paper on the connection of optimal control to this. And now, okay, basically this is a bit more code now to run this as a stochastic differential equation, but from here on it will just be the loss function as before. We train it again, and we get this, which is really nice, because it didn't see, it only saw this, right? It doesn't know that this is a circle, right? There, yeah, it's, I don't know, it's, yeah, nice. And here's a more with very, very many samples from another paper, a figure, where we also had more samples on the sphere, not only 10 here, more, but just to see the full process. So this was the original distribution, just normal distribution, and then at each time how it develops slowly and all the samples are pressed into the right shape. And you get, yeah.
I'm wondering, does he actually learn continuous mapping of these densities, or is it because if you only, let's say you have only 5 t-values, you can also kind of overfit on them so that you only learn from step 1 to the next, or does it really actually also work between these learn samples?
Yeah, so this is also actually in the beginning I always thought, because the formulation is in continuous time, that then you also train the neural network just for uniform t from 0 to 1 and just try everything, which you could do. But of course, because in the end they know exactly how they will discretize the backwards thing, they also only train for these t values.
Yeah, but does it also generalize to unseen t steps before, or does it really only work on these seen t steps?
You mean the network itself? What predicts the norm? I think if you have very small t values, it will just interpolate between the t values. But I'm not the biggest expert on. But yeah, I think so. Yeah. But you don't need it normally, right? You just want the image in the end. I don't know, but maybe if you have an application for it, yeah. Okay, and then one very last thing, the connection to Bayesian inverse problems. I'm not going to go much into this now, but just because this is our most recent work with Youssef Marzouk and Sven Bang from MIT and Sebastian Reich and me. And what we have is basically now you want to maybe sample from something where you have a prior knowledge on your data, which is something maybe like a smoothness class. So you have some physical data now, not images or whatever, but you want to estimate a physical quantity, maybe some initial conditions of a PDE or an ODE or something like this, and you have some prior knowledge. So you want to you think these functions are always twice differentiable. And then you can modify the above algorithms. So for example, these are the functions that we want to sample. So now we really want our algorithm to output samples like this. And the problem is with this original formulation that it adds a lot of noise all the time. And then you will get samples like these, which actually do not respect the smoothness class if you have like a physical thing. Whereas if you modify it a bit, I mean, it also doesn't respect it fully, but mostly because we had to do some trade-offs for numerical stability, but you get samples that are way closer to the smoothness class that you actually want to target. And I thought this is maybe interesting for you in case you have clients with like physical data science problems or something like this. Yes, and that's it. There's a very, very good blog post by Yang Song, who is one of the inventors of it. There were like two people in like two groups inventing it at once, basically. And he did all the connection of this with the stochastic differential equations and stuff like this. And is now associate professor in Caltech, I guess. So it paid off for him. And this is the other paper where the discrete time formulation is. Yes, I think that's it.
Yeah, thank you very much as well for adding this interactive part to our presentations today, showing some code. We have maybe a very short time for one question, if there is one, preferably with a microphone. Yeah.
Yeah, I have a quick question, maybe just an intuition about it. So you said that some of the generative models that generate pictures, you can add a prompt to it. Please generate an image using of two bears. How does the training differ in these cases where you don't want to generate from noise a new image, but noise plus the label I want two bears? How does that work?
Yeah, the obvious next step, that's true, because this was unconditional sampling in some sense. Now you want to actually give some information in, and what you would do is just your neural network now also gets an input for the observation. And what they do, I think, is just, I mean, they have all the images, they have good captioning mechanisms actually, so they know how to caption images automatically, or actually humans do it maybe also, and then they train the networks with both, so they give in the conditioning information, the caption and the image at each point, and then in the reverse process you can just input the caption that you want, and it will basically lead to, it's like, in a bit like you would train a neural network for each different caption, just of course you don't, and that because for a fixed caption you get a fixed distribution again, right? If you say talk at a conference in the style of Monet, this is a fixed distribution of images, so you would just input this to the neural network and then it will lead there. So basically in the training process just always also input that. That's, yeah. And also maybe just want to come back to your question, it's so the main point is here that this path in normalizing flows is variable, how you go from here to here and how you go back, whereas here it will be now fixed. It's very clear how you shall go from here to the normal distribution, and you only learn to reverse this. And this makes it also cool because in this loss function, I only at each time know exactly I want to predict this from this. So basically I can train the neural network at each of the different time scales independently without passing gradients from here through there, which makes it quite efficient.
Okay, thank you very much. I guess if there are further questions or ideas to discuss, you will be around maybe for a bit, or I guess you can contact Jakiw as well. So thank you again for the talk, a very warm applause, and